Yeah, as I mentioned, yeah, we'll finish the iteration today, and then we're going to prove the key estimate in the style of Born-Demeter. We're not going to quite rehash the proof of Born-Demeter for the parabola because, well, one, I plan to do the paraboloid, so it's the 2D version of that argument, and the ideas are also still apparent. So the first half will be the iteration. The second half will be we had a key estimate, 2 plus 4. Last time we talked about how it followed from Plancherel. This time, I'm going to argue it in the way of the Born-Demeter proof style. Okay. Let me briefly close the door a little bit. Okay. Okay, so let me review what the decoupling constants are, just to rehash your memory. So what's d6 of delta? So this is the best constant, such that the L6 norm of f is bounded by d6 of delta, and I'll review the notation. It basically says how much does it cost to break up f into its individual little pieces for all f for A supported in this set. Okay, now let me go off and back up and define things. Remember this guy over here, this is the partition of 0, 1 into ints intervals of length delta. Okay, and what's theta I? Theta I, just by notation, is just the delta squared neighborhood of the piece of parabola above I. And of course, this isn't the only neighborhood of the piece of parabola above I that you could define, but it's the convenient one. The picture, okay, I is of length delta, and it's just literally this delta by delta squared slab. And because we chose a delta squared neighborhood, this is, you should think of really like a parallelogram. Okay, at this scale, I don't really see the curvature of the parabola. And then what does being Fourier supported in this region mean? It means that the Fourier transform of f is Fourier supported in this set. And remember what this set is. This is the set. This is the delta squared neighborhood of a piece of parabola of 0, 1. Okay? Or if you want to draw a picture, zero, 1. Delta squared. Okay, so that's d6. And remember what is our goal? Goal d6 of delta is bounded by delta to the minus epsilon. Okay, and this is notation for a constant dependent epsilon. Okay, and how did we do this? Well, we controlled it by a bilinear term called MAB delta nu. Okay, so MAB delta nu. There are like 4 parameters. So how should we think of what nu is? Nu will be very large compared to delta and very small compared to 1. We'll see today what we choose it as. If you want to know ahead of the answer, it's you choose nu to be delta to the 1 over 2 to the 1 over epsilon. So it's like basically delta to the epsilon. Okay. So secret, later at the end of the proof, nu will actually be yeah. Which you, if you want to ignore this, it's like epsilon. Okay. And then, what is it? This is the best constant. Okay, such that, so secretly there are some parameters here. So this is delta is less than nu to the a and nu to the b. A and b are integers, bigger than or equal to 1. These conditions are just there so that what I write makes sense. So you can ignore these conditions. Best constant such that the integral of f theta I squared, f theta I prime to the 4 is less than MAB delta nu to the 6. So I simultaneously decouple I and I prime into intervals of size delta. Okay, so at this level, it's just MAB is how much it costs to simultaneously decouple these I and these I prime together at the same time into size delta. And the idea is that we want to use some interactions between the F theta I's and F theta I prime. Today will be more clear what I meant by the interactions. Last time we worked with this proof, we really used the fact that the 2 here was just Plancherel. It's very convenient. Today we'll see that the more harmonic analysis point of view, that it's you do really see the interactions between these 2 pieces. Okay, and then there's some conditions about these I and I prime, because if I is I prime, we've done nothing. Okay, the bilinear constant, there's always some sort of transversality condition, so it's the best constant that this is true for all I of length nu to the A, I prime of length nu to the B. The distance between I and I prime is bigger than nu. Okay, bigger than tilde means that maybe it's bigger than 100 nu. We figure out it's bigger than some absolute constant that you can choose at the end. Okay, and of course the standard condition, and for all F, Fourier supported, in the delta squared neighborhood of the piece of parabola above 0, 1. Okay, so let me draw a picture. Okay, so let's draw an exaggerated picture. So let's imagine the delta squared neighborhood of the parabola was the thickness of my chalk, so at least I can draw something. Okay, so here is, let's say, I prime. Here is I. Okay, so I want to break up this piece and this piece simultaneously together at the same time into intervals of size delta. And the distance between here is at least nu, which remember nu is like delta to the epsilon, so you should think of it as pretty large. Yeah. And remember, what was the game? Okay, so I prime is of length nu to the B, I is of length nu to the A. Okay, so remember, what was the game? When A and B is 1, okay, nu is like delta to the epsilon. So these are 2 pretty large intervals. Okay, so that should look like D6, more or less, okay, with some extra separation. Okay, and when A and B are super large, okay, so when A and B are small, MAB looks like D6, right, because I haven't done anything. I'm still trying to decouple large intervals into tiny intervals. And then when A and B are super large, well, nu to the A and nu to the B are then super small. In fact, if A and B were so large that nu to the A and nu to the B were like 5 delta and 10 delta, then then MAB is basically just, if I have this interval of like 10 delta, well, I just use trivial decoupling. Just use Cauchy-Schwarz. I lose like a bounded constant, which is fine. Right? So the whole game here is to go from small AB to large AB efficiently. Right? And last time, we talked about various properties. We talked about 4 key properties. First was that how do you reduce studying from this guy to that guy at some small AB? And then once we're at that small AB, how do we climb up the ladder? It turns out we can go up from MAB to M2BB. There's some numerology, okay? And you've gone up in one of the index, and then we had to swap it. And okay, so let me write down the the 3 key iterative steps, and today we'll see how these all fit together. There's a lot of calculation involved, so some of it I'll just say you can compute. Just exponential, not exponential, geometric series and stuff like that. I'll just say it is what it is. Okay, so iteration. Okay, so this is what we talked about last time, and last time we talked about all the various properties linking MAB and D6. Okay, so first of all, we have bilinear reduction. Okay, what did it say? It said that D6, of course, okay, let me write it down first. Delta over nu plus nu to the bounded. So initially I wrote big O of 1. Today I'm going to write it as just some constant C1. Okay, you can take it to be like 1,000,000. Or if you go through the proof carefully, you'll see what it is. Okay. M11 delta nu. Okay, so what does this lemma say? This lemma says that D6 of delta is either controlled by a better term, right? If this term was always the term that's dominant, this is great because I've just moved up for free, for 0 loss. Okay, so I just keep on iterating. And if this is the dominant term, well, that's also great too because now I've controlled D6 by a bilinear term. Okay, and now, when you write this in mind, you should also keep in mind that, so this basically says the linear decoupling is controlled by bilinear decoupling or multilinear decoupling. Okay, now, if you knew regular decoupling, then you get multilinear decoupling for free. So this is like the reverse inequality. Because if I knew how to already decouple any interval into interval size delta, then I ask how much does it cost to decouple simultaneously? Well, you just pretend this guy isn't there. And then you pretend this guy isn't there, and then patch everything together using Holder. Okay, so this is the reverse inequality. Okay. And then we have the key estimate. It said that if A is less than or equal to B, then MAB delta nu is bounded by nu to the minus C2 M2BB. Okay. And then we had Holder. So here what this does is, so you can think of sort of the easiest, hardest cases when A equals B. And that'll be most of the times when we use it. This basically says BB goes up to 2BB. Okay, so what have I done? I've upped the first index, but how do I up the second index? Well, I let the gain that I've upped in this index flow to the second index. Okay, and there's an estimate from Holder that says that allows us to interchange. MAB delta nu is less than D6. Nope, let's write it this way. MBA delta nu times D6. Okay, so what does this allow us to do? Well, this says, let's say I go from, let's just point at the board and tell you how the iteration works initially. So I start at 1, 1. What does this guy tell me to do? Well, this guy says I can up the first index to twice the second guy. So this goes up to 2, 1. Okay. Now, how do I go up to this guy? Well, I'm gonna use this guy to go from 2, 1 to 1, 2. Okay, and then I'm going to use this guy again. What does this say? This says I can go from 1, 2 to twice the first index. So I go up to 4, 2. So this is how I climb the ladder. Okay, so this allows me to sort of distribute the strength of this lemma onto both the indices. And as for if you write down, and of course the proof of this one is just Holder. The correct Holder is f squared g to the 4 is less than g squared f to the 4 to the 1/2, and then g6. Let's see, 1 plus 3 is 4. Yeah. Okay. And then apply the definitions. Okay, and then there's one last trivial bound that we'll need only when to stop the iteration. And remember, what's the strategy when do we stop the iteration? Well, we stop the iteration when nu to the a and nu to the b are basically of size delta. Okay, and then once the nu to the a and nu to the b are of size delta, then we can just apply like trivial estimates because their intervals is like 10 delta and 5 delta. Okay, and so there's a trivial property. I'll just call it trivial. It's that MAB delta nu is controlled by d6 delta over nu to the a to the 1/3, d6 delta over nu to the b to the 2/3. Okay, and this also follows from Holder. This is Holder with f squared g to the 4, f to the 6 to the 1/3, and g to the 6 to the 2/3. Okay, so this is really only sharp. Remember, so in this game, all your estimates need to have some sharpness to it. Okay, this estimate is only sharp when a and b are super large. Or when a and b are super large, because then I'm trying to decouple two intervals of size delta, and that's essentially what this is doing too. Okay, so at the very end, we'll make use of this. Okay, are there any questions? All right. For simplicity, today I'm going to assume, so I have these less than tildes all over the place. I'm just going to assume that they're all less than or equal to today, so then I don't have to worry about what these constants turn out to be. You, of course, could go through it and be more careful, and you would see that it would also be a constant at the end. Later, okay, I guess I do keep writing new inverse to the something, but I won't keep track of how the constant depends on C2 and C1. Okay, you can also keep track of. I'll probably write new to the big O of 1 throughout. Okay, so let's do the iteration. This will be kind of tedious. Okay, so we start out with M11. And of course, I'll stop writing the delta comma new. So I'm going to write M11. Okay, what does M11 say? Well, M11 by, okay, I guess I labeled them in my notes. So let's call it 1, 2, 3, and 4. Okay. Okay, by 2, M11 is controlled by negative C2, M21. Okay, once I do by 2, I need to use 3. Okay, and then by 3, C2 times M12 to the 1/2 D. And also I'm going to be lazy and drop writing the 6 because it'll be implicit. Okay, I'm going to just write D of delta rather than D6 of delta. Okay. D of delta over nu to the 1/2. Okay. Now what do we do now? We're gonna use 3 on M12. Okay, so if I use 3 on M12, or 2, I'm going to use the key estimate. I get nu to the minus C2 times by nu to the minus C2. What does 2 say? 2 says the first index can be upped to twice the second index. So twice the second index is 4. Okay, M42 to the 1/2 D of delta over nu to the 1/2. Okay, and then now you can see that C2 is going to be another, like, C3, that's going to be like twice C2, okay, because this is 1/2, and you can already see a geometric series happening. Okay. And then what do I do now? Well, okay, so let's rearrange. Let's now use 3 again. 3 allows me to swap this 4 to the second index, and now I've gone from like 1, 1 all the way up to 2, 4. Okay, so this says nu to the minus C2 minus 1/2 C2 M24 to the 1/2 D of delta over nu squared to the 1/2 to the 1/2 delta over nu to the 1/2. Okay, and let me write one more. Let's rewrite what just happened. This is, okay, I'm going to say nu to the bounded, even though it's clear what this constant is. Okay, M24 to the 1/4 D of delta over nu squared to the 1/4 D of delta over nu to the 1/2. Okay, so you've seen at least like 2 iterations. Okay, and then it should be clear on what to do. So then you create a parameter n. N is the number of times you up this. Basically, you up this all the way up to like 2 to the n. Okay, n is a parameter chosen later. Okay, so you continue this process. You continue it. Let's see how to do it. Dot, dot, dot. Okay, and what do you get in the end? Less than nu to the minus big O of 1, and this is going to be different, a different constant. Okay, this will be like twice C2. Okay, times m 2 to the n minus 1, 2 to the n, delta over nu to the 1 over 2 to the n. Okay, and then you're going to aggregate all these little terms when you iterate n times. And you get a product, j equals 0 to n minus 1, d of delta over nu to the 2 to the j, 1 over 2 to the j plus 1. Okay, and if you check that when n is 2, you get this, and then you're like, ah, okay, so I haven't made any typos. Okay, so this is iterate n times, and n is a parameter chosen to be dependent on epsilon later. Okay. Great. N chosen later. And really, so in retrospect, you can sort of see that this iteration is going to work is that you've sort of doubled the indices while like halved the power. And sort of there's some sort of balance. Now, I don't think there's really that good of like a study of like, okay, when do iterations work other than you just have to try enough and then it works. Yeah. Yeah, but you can sort of see that this might work because you've doubled the indices and you've halved the power and you've distributed it. But that's kind of a, like, you know, reading the tea leaves way to see how iterations work. So it's not a rigorous thing. Okay, so we have probably a pretty good estimate. The only way to tell is to actually try to finish it. Okay, so now what do we want to do? Great, so now we think that we chose n super large. Okay, so large so that like nu to the 2 to the n is like delta, and so like nu to the 2 to the n minus 1 is also basically like delta except, you know, with some small power that's negligible. Okay, so now it's then efficient to use step 4, the trivial bound, on this term over here, because this is a term we get, this is an n, we've chosen one of the terms so that at least it's like size delta. So now at least the estimate will be efficient. Okay. So let's use that estimate. Okay. Okay, from 4. Let's say this one is less than. Okay. Okay, so what do we have? M11 is controlled by this guy, and this term over here is controlled by this guy. Okay, great. So remember, n we choose to be dependent on epsilon. So anything we can choose. Now, we haven't chosen nu yet. Right? I've secretly told you what to choose nu as, but right now we don't know. Okay? Now what do I want to do? Well, let's just choose nu so that delta is nu to the 2 to the n. Right? Then this is like d of 1. So d of 1 is easy to compute, right? If I give you an interval of size 1, and maybe by 1 I mean interval length 1/2 or something, or a millionth, okay? You know, how much does it cost to decouple 0, 1 into intervals of size 1? Well, it costs 1. Okay, so we're going to choose, this says, choose, okay, nu such that, well, choose nu to be equal to delta to the 1 over 2 to the n. Okay? Okay, so let me write down. Okay, so nu is now chosen to be this guy. Okay. And so let's just plug everything in. We now know what nu is. We know what this guy, an upper bound for this guy is. Okay, and let's just plug in nu and get some exponential stuff. Okay, so therefore, then, okay, then M11 is less than, and I'm ignoring, you know, secretly I should have less than tildes and they would slightly pile up, but it's an exponent, you know, they pile up like the C2s, right? It gets halved and so there's some exponential sum, not exponential sum, geometric series. Yeah, so anyways, you get this times delta to the minus, let's call it C3 over 2 to the n. Okay, this is the nu to the big O of 1. Okay, times d of delta to the 1/2. This comes from this guy. To the 1 over 3 times 2 to the n. The 1/3 comes from here, but remember, this term is raised to the 1 over 2 to the n. Okay. Times by product, j equals 0 to n minus 1, d of delta to the 1 minus 1 over 2 to the n minus j to the 1 over 2 to the j plus 1. So there's some mess. Okay. Great. Now, Okay, so this is the bilinear term. Okay. This is the bilinear term. And actually, if you compare, as a little exercise, you could compare this term with sort of what would you get out of, let's say, using almost multiplicativity. And you'll notice that you get a small gain. But I won't do that exercise. Now, let's use bilinear reduction. So we have a good estimate on M11. And what do we say? We said D6 is controlled by D6 over nu. And nu we now know. We've chosen nu to be delta to the 1 over 2 to the n. Plus this thing, which is also delta to the minus 1 over 2 to the n, times M11. Okay. So apply 1 to get what? Okay, so we get D6 is bounded by, and I'm going to ignore the tilde, d of delta to the 1 minus 1 over 2 to the n, plus, let's say delta to the minus, let's say C4 over 2 to the n. That's just C3 plus whatever powers of plus C1 pretty much. Okay, so there's some other constant. Okay. Times by this guy. J. Okay. So now you have an iteration. So this is what decoupling says about d of delta, where n is a number you can choose. You pick n equal 1 if you wanted to. You know, but that's, you'll realize that the iteration you get is not very good. Okay? So n is an integer that you're free to choose now. Okay?
I'm confused. The first thing is delta over 2 because delta 1 over...
Yeah, so the first term, remember, is delta. The first term is d of delta over nu.
Oh, nu.
Yeah.
Not 2. Sorry.
Not 2, over nu, right?
Sure.
And nu is delta to the 1 over 2 then, so I plug this in. Right?
I saw it's 2. Okay.
Yeah. So then it here becomes obvious that like this is a really good term, right? Because this just says I can go, I've moved to a larger scale for free, right? Imagine if n is 1 first. That basically says d of delta is bounded by d of square root delta, which is great. I've like moved from like to a larger scale for basically free. Okay. Okay. So n is a number that you can choose now, and great. So now we gotta let's think about what to choose as n. So this estimate is true for all n and for all delta. Oops. Okay, so great. So we want to prove that d of delta. So want to show that d of delta is bounded by delta to the minus epsilon. Okay. Let's say let's let lambda be the smallest number. So you don't have to argue this way. You could just, this is a recursion, right? You could just argue, just use the recursion. Okay, let's do a proof by contradiction. Okay, so I'm going to let lambda be the smallest number such that d of delta is bounded by delta to the minus lambda minus epsilon. Okay, this number exists since lambda is at most 1/2. The trivial bound is so. Okay, lambda exists because trivially d of d6, d of delta, is bounded by delta to the minus 1/2. Okay, so there's at least the smallest number, and it's also non-negative. Okay, and so if lambda was 0, then we would win, right? So let's assume lambda is positive. So if lambda equals 0, great. Let's draw a better check mark. Okay. If lambda is positive, we're going to derive a contradiction. Great. We're basically going to say that, well, if lambda was positive, we're going to use this iteration to show that we're going to get a better estimate for d of delta, right? This lambda over here is the best estimate on d of delta, d6, that I could have. But it turns out that if I plug it in here and choose my n appropriately, I'm actually going to get an even better estimate. So therefore, I can't ever have lambda being positive, being the smallest number. The only valid lambda is when lambda equals 0. You can make this quantitative if you want, but this is the easiest way. Okay, great. So we have this guy, and let's assume that lambda was the smallest guy such that this estimate is true, and let's also assume that lambda is positive. Okay, well, we have all the data. Let's plug it in. Right? So we plug it in. What do you get? Which board is? Let's keep this one up. Let's erase this one. Okay, so what do we get? Let's just take d of delta is less than delta minus lambda and put it in here. And what do we get? Okay, use d of delta. Let's call this star. Put into star and get. What do we get? We get d of delta is bounded by, well, you just plug it in. So the first term gets me delta to the minus lambda times 1 over 2 to the n minus epsilon. That's smaller already. Okay, but what about the second guy? Plus delta to the minus c4. Okay, c4 is like, 100 over 2 to the n times by, let's see, so you plug in this guy. So this gives me delta to the minus lambda over 2 times 1 over 3 over 2 to the n. Okay, so this second term over here gives me a delta to the minus lambda over 6 times 2 to the n. Okay, this term over here, the 6 over 2 to the n comes from this guy. And then when you compute what this is, so you're going to get, you take each of these terms, put in a delta to the minus lambda in it, okay, and then you're going to get a geometric series. Okay, and let me write that down. So let's see. So is there a color? Okay, great. There are multiple colors. Okay, so this term, and then this term, those correspond to this term and this term. Okay, and then the white term over here will correspond to the white term over here. Okay, and then the last guy, you'll get a delta to the minus sum j equals 0 to n minus 1, 1 minus 1 over 2 to the n minus j, 1 over 2 to the j plus 1 lambda, delta to the minus epsilon. So here you're going to get a white term. Just plug it in. Okay, so now you have to wonder about what this sum is. Okay, so you have to combine everything over here. And hopefully it's actually less than this term, because if it's less than this term, let's say this guy was less than this term. Then what has happened? We have just shown that d of delta is less than this guy. Let's say we chose n, so that this happened, so that this guy is less than this term. Then what did we do? Let's say n is 1,000,000. Okay. Then we've shown that actually, if we knew that d of delta is less than delta to the minus lambda, then inserting it into the iteration, we have then shown that d of delta is bounded by delta to the minus lambda times 1 minus, 0.001. So this is like delta to the minus 0.999 lambda. And so lambda is not the smallest possible lambda. 0.99 times that term was. Okay, and then, well, that's bad, right? Lambda was supposed to be the smallest. Okay, so that's actually what we're going to do. You can actually compute this. Okay, you compute it, and I'm not going to do it in front of you. So you compute these three terms, and what do you get? You get delta to the minus lambda. I want to try to make it look as much as this term as I can, times, and let's use appropriate brackets so it becomes obvious, 1 minus, okay, 5, 6, n over 2 minus, I believe C4 over lambda times 1 over 2 to the n brackets minus epsilon. It's just, you do the algebra and you get this. Okay, and n is a number we can choose, right? N is a number that we're free to choose to be whatever we want. Okay, so we're going to choose, let's write it here, choose n such that 5 over 6 plus n over 2 minus C4 over lambda is at least 1. Because if it's at least 1, let's say it's at least 10, and this is basically like 10. And so that means this term is actually bounded by this term. Because so, then, d of delta is bounded by delta to the minus 1 lambda 1 over 2 to the n minus epsilon, where n is this n. Okay? And then this is a contradiction. Contradiction. Because lambda was supposed to be the smallest. Okay. Now, of course, it's not hard to see that in this proof that, how to make this quantitative. You put an epsilon here. And so n is going to be in the end like 1 over epsilon if you want to prove that d of delta is less than delta to the minus epsilon. So in this iteration, you iterate about 1 over epsilon many times to prove decoupling with the parabola. Okay. Great. So that shows at least the iteration. So when I talk about the paraboloid, I'm just going to say the key estimates and say that the iteration works. Okay. Yeah. Are there any questions? Yes.
I think I have a question.
Uh-huh.
I think this method is somehow clever that you have to guess it first. You have to. I mean, you just get it somehow like your iteration, and we have a recursive inequality.
Yeah.
Yeah, but now you just get you have this such I mean d delta
Like
want to show. I mean given that recursive inequality, it's not clear why it's not naturally that we can guess such
an make a guess. I mean, yeah. I mean, it's not obvious. Like if I write this down, and you can write down lots of things, and you'll get a recursion. But it's not always true that like whatever recursion you're down will actually win in the end.
Yeah.
Right. So like this turns out to be the right iteration. So then that implies this. Now you don't have to make this guess. You could just derive it from this recursion over here. Right.
So I think the basic question is how we derive that recursive inequality. I mean before we derive this recursive inequality, we do one more time. We do one more induction. We do one more iteration.
Yeah.
In your iteration there. So I just wondered if there's any intuition how we do this iteration. So I think the strategy is the first we do iteration, and then we got the recursive inequality.
Mm-hmm.
And then by contradiction
We show that the estimate is small. Yeah.
Yeah, but
So you're asking how to build the iteration.
yeah, I mean it looks like a miracle that
I mean, it is.
yeah, if you don't compute then you don't know the result.
Yeah.
But I think there must be some simpler argument that if we don't do this complicated argument, we can get some weaker result. And then we do complex argument, we can improve this weaker result. And the best result is the optimal one.
Yeah, so one thing to use, so we had, okay, these 4 steps are here. I mean, so sort of the key guiding principle, I guess, in trying to, I mean, you know, in decoupling proofs, a lot of it still is like, okay, you just sort of try it off, okay? And you can sort of see that this might win ahead of time in that this estimate really is sort of sharp in the sense of you really try to squeeze out all the data about from going from A to 2BB. This followed from a certain bilinear estimate where we decoupled the square using Plancherel. And this sort of in a later language is using information about the line, right? So why did this proof work? Why did the key estimate work? Well, it worked because we have the parabola over here, and we sort of were, you know, we have a little partition here, and then we project it onto the y-axis, and these were almost orthogonal on the y-axis, if you remember the proof. And there, what we sort of did was we sort of used line decoupling. We used the fact that there's some decoupling on the line. We used some sort of lower dimensional data, right? In the proof of this key estimate, we only use Plancherel in the vertical direction, right? And that's using some sort of lower dimensional input, right? We didn't care about where the x support of these little pieces were. We only care about the y support, okay? And there's some lower dimensional input. And in all decoupling proofs, there needs to be some sort of multilinear reduction and then some sort of lower dimensional input, and then you just hope for the best. I think that's there's not any like magic formula to tell you ahead of time, if I give you a surface, what estimates do you need to prove so that you can prove what decoupling estimate you need. It really is just, you just try. And then you need to make sure that every one of your steps is generally sharp. You've used all the lower dimensional data that you need, and then you just hope for the best and try. There are times when you think that you have all the estimates, and then you iterate, and you lose just barely. And there's nothing that, at least from my experience, that tells you ahead of time that you're going to lose. Yeah. Yeah.
The question,
Mm-hmm.
just following just mentioned, you mentioned something like multilinear.
Mm-hmm.
So I wonder if you have try something. For example, you use Bilinear constant, break the 6 to 2, 4.
Mm-hmm.
Now, is anything like trilinear, like 2, 2, 2?
Mm-hmm.
And sort of this method.
You could try trilinear, I guess, with 2, 2, 2. It just seems a bit unnatural to do trilinear in 2 dimensions. I'm not saying it won't work. Yeah. Yeah. I mean, and I'm, in the Bourgain-Demeter-Guth moment curve proof, the Bourgain-Demeter argument did a n factorial linear argument because they needed enough multilinearity to use their multilinear Kakea. And in the short proof that Polem, Xiaoming, Pavel, and I had, we actually have, it's all bilinear, which was surprising because the moment curve in Rn lives in Rn, so I would at least want, maybe it suggests to say that, okay, maybe I should just use n linear as my multilinear decoupling estimate. But the way the efficient congruencing proofs do work is that they actually have n different bilinear constants, and they all interact with each other, and you get this nice pretty iteration with this matrix that obviously has eigenvalue 1 because it's a Markov matrix. So, I'm not saying that if you do 2, 2, 2, it won't work. It's just no one's tried. Yeah. 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 Are there any other questions?
Yeah, so
Uh-huh.
One more question.
Uh-huh.
So what if the case, yeah, so I mean, is there any case that decoupling constant for some manifold that if lambda is actually positive?
Oh yeah, I mean.
Then in this case, does this kind of method still work?
Oh,
I mean, how to guess the correct lambda here?
Yeah. So of course here d of delta. I've already erased it, right? Remember d of delta is L2 L6 decoupling, right? It's L2 L6. Of course, I could have L6 L6 if I wanted to. And there I would lose the positive power of delta as the sharp estimate. Right? So then what would I do at this step of the argument is I wouldn't consider, d of delta. I would renormalize it by whatever it would be. So let's call it cursive d of delta. Okay? And I expect cursive d of delta to be something. Okay, let's say I expect delta to minus alpha in the end. Okay, then I would run a similar iteration, and then over here, what I would define, I'm going to define, let's say, d prime of delta to be equal to cursive d of delta divided by delta to the minus alpha. Okay, and then I make the assumption that it's delta minus lambda minus epsilon, and then you rewrite your iteration in terms of d prime of delta, and then, yeah, then it's the same argument. Uh-huh.
Yeah, so for this is x, our lambda is 0, but for p other than 6, you must have that power.
Is in p bigger than 6?
Yeah.
Yeah.
Yeah. So for example, can this argument be applied directly to d8?
Yeah. Yeah, so there are some small changes you'll need to change. First of all, you're going to have to think about which bilinear estimate to use, right? Do you want to do 2 plus 6? Then that won't work, actually. The right estimate to use here, so this relied on the fact that this is 2, and then you really use line decoupling on the y-axis. So what you can do here is if you want to do 8, well, you can put a, let's see, so it will be dictated by, let's see, there is a particular, what you can do. So to guess the right bilinear estimate over here, you could say, well, I'm going to put a p and then an 8 minus p here. And then L2 LP line decoupling is known, not just at 2, but you can interpolate between the p equals 2 and p equals infinity estimates. And then you run through the proof, and then you'll have an extra parameter p to optimize, and then you get to choose the p. I don't know what it is off the top of my head, but it should be doable. Yeah. Yeah. Are there any other questions? Okay. Great. So for the rest of the lecture, so I guess I want to make some remarks, and then maybe we'll break for a little bit. Great. So we've proved this, right? We just proved this result, and okay, so if you work through the proof carefully, by carefully working through the proof, Okay, you can actually improve this to d6 of delta is less than exponential some constant times log divided by log log. This is this is sub-exponential, it's slightly better than this guy, right? The comparison is that, remember, this is exponential of epsilon log 1 over delta. Okay, just to make it obvious, ignoring this whatever thing. Okay, let's put a constant here. I don't know. Okay, you can actually just go through it, and this is a result due to me. L probably 18. It's now an exercise in Terry's 247B notes. There is the example, okay, Bourgain, GAFA 93. And Bourgain showed that d6 of delta is at least log to the 1 over delta to the 1/6. Okay. So these two bounds have a lot of, it's pretty far away, right? This is exponential log log, almost. This is exponential log over log log. Okay. And recently, so what's the best upper bound? Best upper bound in R is due to Larry Guth, Dominique Maldog, and Hong Wang, who showed that d6 of delta is bounded by log to the 1 over delta to some constant. It's like 200. They didn't work it out, but I believe I once tallied, and it's at least 100 or 200 or so, and then Hong told me that it's probably like 200 or so. Anyways, they have some wave packet tails that make it a bit messy. Okay. Great, so that's the end of the story for D6 for now. Okay, so maybe we'll take a short break, but when we come back, I want to talk about wave packet decomposition and a different proof of this estimate over here. This used Plancherel. It's almost too nice. It just uses lower dimensional decoupling in the sense of it uses decoupling, or Plancherel, decoupling for the line is just Plancherel. It uses decoupling in the y direction. Okay? I'm going to give a proof that uses sort of the uncertainty principle in wave packets, which is the more traditional proof. Yeah. All right, so let's break for 5 minutes and then we'll come back. Parabola, the iteration is what it is, but this proof of parabola decoupling is somewhat special. It's quite different from, I'd say, most other decoupling proofs for surfaces, though it's very similar to the short proof of the decoupling for a moment curve that I have. Okay, let's prove the key estimate here in the style of Bourgain and Dambeter. And to do that, I need to introduce wave packet decomposition, the uncertainty principle, and sort of the local constancy property. And these are all heuristics. Okay. Maybe I'll erase this one too. Okay, so we go back to doing heuristics. Now remember in our heuristics, the phase heuristic was a thing, right? Remember that, so we're going to use this today again. So we're going to use the phase heuristic. All right, what did the phase heuristic say? E of theta, remember this was e to the 2 pi I theta, is equal to 1 if theta is small. Okay? Of course, if you don't like this in the real world, you could work in QP, where this is fact. And of course, another thing we did was we assumed that if a ball radius 2r, well, we don't care about the 2. That's basically a ball radius r. and a ball of radius r, the center. So a ball of radius r is the same as, I'm going to call this a ball of radius r, and I'm going to call this a ball of radius r, and I'm going to call this a ball of radius r. Right? These don't matter. This is also true in QP. Okay. Assuming your prime is big enough, but anyways. Okay, so let's, and we'll use lots of pictures. Okay, so local constancy property. Okay, some people, all of this is under the umbrella called the uncertainty principle. Some people say by the uncertainty principle. If you talk to people who, especially those who are influenced a lot by Larry's papers, they'll call it the local constancy property. Let's write it down. Okay, so let I be an interval of length 1 over r. Let's say in 0, 1. 0, 1 is not so important. Okay, it's just that this is the situation we're working. Suppose G is for A supported in P. Okay, P is standing for the piece of parabola. So lots of P's, so I'm going to call it P. It's the neighborhood of the parabola that lives above I, and it's the 1 over r squared neighborhood. Okay, it's literally the piece, it's the parallelogram that lives above I. Okay, so let's draw a picture. I, okay, 1 over r squared by 1 over r. Okay. Great, so G is a function whose Fourier transform lives in this region. In this yellow region. Okay. What do I know about it? Okay, we're going to let T0 be all the points in R2. Now this won't be rigorous, but it is rigorous if you place R with the p-adic field. Okay, and it is rigorous if you make enough changes. It's morally true. Okay. Such that y1 plus 2ay2 is less than r, and y2 is less than r squared. Okay, let T naught be the dual tube, the dual tube, 2p, where T naught. Yeah, T naught. Where A is, say, the left endpoint of I. Okay, so here's this rectangle. I'll draw it's a parallelogram, but I'm going to call it R2 for a rectangle. Okay. We call it the dual tube to P centered at the origin. It contains the origin. Where A here is, let's say, the left endpoint of I. It's not important that it's either left or right or center or any point. Just pick any point in I. Okay. Now let's draw this picture. What's T naught first? Okay. Okay. So this guy. Okay. So I'm going to pick the left endpoint here. Okay. This is A. There is a normal direction attached to A, right? Let's take this direction over here. You can compute what it is. Okay. What's T naught? Okay, T naught is this rectangle. T naught, not because it's centered at the origin. Okay. Naught is this rectangle that is r by r squared pointing in the same direction. Okay, maybe I can denote that there's the same direction by drawing them in color. Okay. Strictly speaking, this is a parallelogram, but I can dilate it, and twice this is contained in one of these. And yeah. Okay? So, long direction 1 over r, short direction r. Short direction 1 over r squared, long direction r squared. Okay? These are dual. Okay? So, that's P. This is P. And this is T naught. Okay? Now, I've only defined things. Okay. What's the conclusion? Then, absolute G is, quote, essentially constant on any translate of T naught. And when we do these these sort of proofs, we often just, essentially constant. Okay, well, it's basically constant, so let's pretend it is constant. Okay. Now, some remarks. Yeah. Okay. So first of all, this essentially constant quotes means that this is only heuristic. Okay. Now, of course, you could make this rigorous. There are multiple ways to make this rigorous. One way is that you work over QP. Then you delete the quotes and the essentially part. It really is constant. Okay. Another way to make this rigorous is to convolve it. I'll talk about this in a little bit. Okay. Great. Okay, so let's make some remarks. We've almost seen this lemma before. So remark 1, compare. We've already seen this. Remember, in our first lecture, so theta I here was I is an interval length delta. Theta I, remember, is the delta squared neighborhood. Okay. This was the theta I delta squared neighborhoods of the parabola that we just talked about. What did we compute this as? Well, this guy, the Fourier inverse, is this oscillatory term. It's the volume of the theta i's times the dual tube. And remember, the notation was okay, so this is theta I. And then the dual tube, T naught I, is delta to the minus 1 by delta to the minus 2, centered at the origin. Okay, this is a calculation we did in lecture 1. And let's compare with what this says. Okay, let's pick R to be 1 over delta. Okay, if we pick R to be 1 over delta, then this calculation does not contradict this, right? This, because the absolute value, what's the absolute value of this guy? Well, this term is gone, and this is like, I don't know, delta cubed. It's like 5 or something. Okay, so the absolute value, so G, in this example, you take G to be this function. G is essentially constant on any translate of this tube. Well, that's true, because it's literally 1 on this tube and 0 elsewhere. Right? So we've seen a slightly different version of this thing, right? Like, this is true for all G whose Fourier transform is supported here. And for that particular G, that's the indicator function of 1 theta I Fourier inversed, we can actually do better calculations. We actually know what this constant is on various translates. It's 1 on its dual tube and 0 elsewhere. But if we don't know anything about G, then I can't compute anything. Okay, and all I can say, well, it's constant. So I have no control, in the general case, I have no control what the constant is. But oftentimes, knowing that it's a constant is good enough. Okay. So you've almost seen this before. So that's a nice remark that it matches some older heuristics. Okay, 2. In particular, the local constancy property also implies that the absolute value of G is essentially constant on any ball of radius r. Okay, so let's remember when I say ball radius r, I could mean any three of these objects. Okay, they're all the same under this heuristic. Okay, so why? So given this local constancy property, if I study absolute G, and G is Fourier supported in this 1 over r by 1 over r squared neighborhood of the parabola, why is, given any ball of radius r, why is absolute G essentially constant on it? Well, let's take a ball of radius r. Ball of radius r. I feel like if you taught calculus like this, people would already be complaining. It's a ball of radius r, okay. Any ball of radius r. Well, any ball of radius r, I can find a translate of T naught. Right, I don't care about 2r or r. Sounds like it's a, it could be a million r by a million r squared. That's the same as this. I can always find a translate of T naught that eats it up. Okay? So let's say this is C. Then I'm going to take the translate C plus T naught. This is an r by r squared tube, translate of T naught, that contains this ball of radius r. Now, by the local constancy property, absolute G is constant on this whole tube. It's 5 on this whole tube. And so therefore, it's constant on this ball of radius r. Right? And so then this is true. Okay? Okay. Great. Okay. So those are these are sort of two important remarks I want to make before I argue why should this be true. And the proof will be using the phase heuristic. Okay. Okay. Proof. Okay, so why is absolute G essentially constant on this translate of T naught? AB is arbitrary. Okay, so we just need some notation. So we're going to let MA be the matrix 1, 2, A1. It's a shear matrix as determinant 1, though, so it's volume preserving. Okay. Then MAT naught, by definition, is just I'm going to take any point in T naught. I'm going to apply this matrix to it. And of course, because of how T naught is defined, this is going to be the matrix. This is going to be the rectangle. That's going to be this rectangle. R squared. Right? Just take any point in T naught. That's y1, y2. Times it by MA. You're going to get a point that lives in here. Okay, so this is a vertical r by r squared rectangle. Okay? So I want to ask, why is this guy constant on this guy? Well, I can just apply MA to everything and ask it, why am I constant on this guy? So let's rewrite the question. So, why is, okay, so then it gets kind of annoyingly notational. X plus AB constant on T naught. Okay, and then you apply this fact. Okay, so I guess I should have reversed the sentences. So, y is, okay, G of M inverse A plus AB parentheses, absolute value, constant on this vertical tube. Same question. I've just applied matrices. Okay. So I've done nothing so far. I've just applied linear transformations to make my tube straight. Okay. So why is that true? Well, at this point, you have to do something. You've done nothing so far. So, for simplicity, because I don't want to write too much, so at the next step, you're going to have to write out what G is. Because you know G is Fourier supported. The Fourier transform of G is supported in P. Okay. So now you really have to use what G is. And for simplicity, I'm going to assume AB is 0, because otherwise it notationally becomes very hairy and it's the same proof. Okay. For simplicity, let's assume AB is 0. Okay. So then we just need to ask, what is G of MA inverse of X? Okay, great. So, what do we know about G? We know G is Fourier transform supported in P, and P is the 1 over R squared neighborhood of the piece of parabola that lives above I, and I is the integral length 1 over R. Okay, and the left endpoint is A. So let's just write that. We know that this is the 1 over R squared neighborhood of the piece of parabola that lives above R. Okay, and then E of, oh, I didn't write E of, okay. Yeah, okay, let's do it this way. S times x1 minus 2a x2 plus s squared times x2 e of tx2 ds dt. Remember here, e of z is e to the 2 pi I z. And I want to close absolute value. Okay, you just plug in what it is. Okay. And what do I want to do next? Well, I'm going to, well, I is an integral from a to a plus 1 over r. So what do you want to do next? Well, you want to shift a to be the origin, okay? Okay, so let me just write down what happens. Okay, so you're going to get minus r to the minus 2, r to the minus 2, 0 to 1 over r. Okay, you're going to get g hat s prime plus a, s prime plus a squared plus t, e of, let's say, let's see, how do I want to organize this? I want to say s, okay, let's do it this way. Oh, I see what I did. Okay. Okay, let's do it slowly, and then we don't have to, then we can just do it. ds prime dt prime, okay, so all I've done is put the a in. And then what do I do? Well, I say, okay, so I'm going to gather up the s primes. Okay, so then what do I get? I get s prime x1 minus 2 s prime ax2 plus s prime squared x2 plus 2a s prime x2, and then plus a times x1 minus 2a x2 plus a squared times x2. Okay, you've expanded everything. And I've collected the a's. So s prime x1 minus 2 s prime ax2 plus ax1 goes here, minus 2a squared x2 goes here, and then s prime squared x2, 2a, and then a squared. Okay? Now, this term, this last term over here, gets killed off by the absolute value in the end. Right? Because it's not integrated over, and a is a number. Right? This is e of e to the 2 pi I times this expression over here. Okay, so that gets killed off. Okay, great. So color, no. Okay, now it looks like an X, but okay. And then this term is the same as this term, right? Okay, so what do we have left? We have s prime x1 plus s prime x squared x2, right? So let's write it down. And I've written too big, so where should I write? Well, okay, I'll continue to write here then. Okay, so what's happened? So this is just minus 1 over r squared, 1 over r squared, 0 to 1 over r. To save space, some stuff about g that's not important, times e of s prime x1 plus s prime squared x2. Yes, I forgot the e of t prime x2 over here still. And then e of tx2. Sorry. Yeah, there should be no t prime tx2. ds prime dt prime. Okay. Great. So we've just changed variables. Are there any questions so far? Okay. Now we need to use the fact that we live on this space. All right. So, okay. So let's get rid of this term first. So t is of size 1 over r squared at the origin. x2 is of size r squared. So what's t times r squared? T times x2 is less than 1. So what does our phase heuristic say? Phase heuristic says that if it's less than or equal to 1, there's no oscillation at all, so I get to ignore this term. Okay. And then let's look at this term. S prime times x1. Well, S prime lives between 0 and 1 over r. x1 lives between 0 and r. So S prime x1 is also less than 1. And what does our phase heuristic say? Well, it says that if it's less than or equal to 1, we get to ignore it. So you get to cancel off this guy too. And similarly, well, S prime squared is 1 over r squared. x2 is of size r squared. So S prime squared times x2 is also less than 1. Great, we get to cancel off all our oscillation. Okay. Of course, you know, the g hat also has stuff in t. Right? So I don't immediately get rid of the integral in t or s. Right? But nonetheless, what does this say? This says that this guy is constant on this rectangle. What constant is it? Well, it's a constant that depends on g. It depends on whatever tube you're looking at. And it's a constant depending on a. And it's a constant that depends on everything. It depends on p. It depends on the particular translate. It depends on g. But nonetheless, it's a constant. Okay? Assuming the phase heuristic. Okay? Which, if you work over QP, is rigorously true. Okay, so that's one way to make this rigorously true. Okay, so are there any questions for this point? So this is the key heuristic that everyone uses as a first pass when they do their arguments. Okay, great. So at least it seems plausible that this heuristic could be rigorously true, and there are ways to get around this. So of course, one way is to work in QP, and then life is easy. But if you insist to work in R, this is a little analysis exercise, I guess. Okay, so how do you make this rigorous over R then? Okay, we kind of just threw away our oscillation like it didn't matter. Great. There are different ways to make this rigorous, and oftentimes it really depends on the problem. So this is also one way or one reason why in this literature there's not really a theorem in the literature that says if you assume the uncertainty principle and prove these estimates, then it's rigorously true. There's no such theorem that says you're free to use this, right? Often the way to make this rigorous is that you first write your paper using the uncertainty principle in various different ways, and then you sort of aggregate which places in your argument, they might need different versions of the uncertainty principle. And then you have to sort of modify your argument slightly, and there are going to be different expressions that are essentially equivalent under the uncertainty principle, but rigorously they may be more convenient to use. So for example, one way to make this rigorous and I like this way better. In R is to consider G convolve phi of T naught, where phi T naught is 1 on T naught and rapidly decaying outside T naught, and L1 normalized. Because it's L1 normalized, the integral of this guy is the integral of G. Okay, and you can show, so there's a particular phi T naught that you do have to use. It sort of explains, if you ever look in the rigorous proofs of decoupling, they always have some sort of like 1 plus a certain term to the minus e. Okay, this phi will look like something like this. Okay, I can go over more details later if anyone is interested. But this guy will be up to a multiplicative factor that's uniform, constant on any translate of T naught. Okay, so what happens often is that you'll need to convolve G. One way to make this rigorous is to prove estimates where instead of writing G, or earlier we wrote stuff about like f theta I squared times f theta I prime to the 4, right? Instead what you would do is you would say, well, okay, I'm going to actually work with estimates that look like f theta I squared convolve some particular function that's adapted to T naught, okay, to the dual of theta I, the Ti naught, let's say, and then times by f theta I prime to the 4, Ti prime naught. Okay, you work with these slightly messier expressions. These guys are up to multiplicative, up to like 1/2 and 2, bounded above, a constant that's bounded above and below, truly a constant on any translate of this dual tube. And then you could run the same arguments for these guys, and then what you would have to do is you'd have to link these estimates to regular decoupling, which is not hard because this is L1 normalized. Okay, but that'd be like another 20 minutes. That's one way to make this rigorous. If you want a source for doing these estimates, I believe in one of the links in the lecture in the announcement pages on the NCTS website, there's a paper by Polam Young, Xiaoming Guo, and I called Bilinear Proof of Decoupling for the Cubic Moment Curve that we do make it rigorous by using this convolution thing. Okay, and you of course could use that everywhere. There are other ways to make this rigorous, but yeah, this is one way. Yeah, so I just want to say that it can be done. It's not just nonsense. But that's not the important remark. And as you see, if I had introduced it this way, it would be, it introduces a lot of unnecessary complication. Why am I convolving with these things? Okay. Okay, so if you want to make it rigorous, well, oftentimes the way people do these proofs is they do the proof assuming the uncertainty principle. At least they make it has to at least go through assuming this property. And then you have to go through and carefully work through and make everything rigorous, and then by the time it's completely rigorous, it might look kind of different from your original proof, but at least morally it's still equivalent. Okay. Another thing, okay, so that's a side remark. You can make this rigorous. Okay, what's the more important remark about the local constancy property? Okay, so G is Fourier supported in P, and I know that absolute G. So let's pretend that so I'm going to not even put quotes here, but when I say essentially constant, you're going to think of it as under the uncertainty principle. G is essentially constant on any translate of T naught. Great, so I know what T naught is. Why don't I just tile R2 by T naught, translates of T naught? Right, so tile R2 by translates of T naught. Okay, so all directions. Then what does that say? Well, I know that absolute G is, a constant here, a constant here, a constant here, a constant everywhere. I mean, it's a different constant. It's a constant that depends on P, it depends on G, it depends on which tube I'm looking at. But nonetheless, it's a constant, right? So I have some structural data about G. I know that at tubes at this scale, absolute G acts like a constant. Okay, so we have what I'll call wave packet decomposition. Sometimes wave packet decomposition also comes with a little oscillation, but I'll slightly abuse the terminology and ignore the oscillation. But so let G be Fourier supported in P, on P, and let Ti, okay, remember I is the interval that P lies above, be a tiling of R2 by translates of T naught. Then there exists constants Ct, and this Ct also depends on G and basically everything, okay, such that absolute G acts like the sum of these tubes. Okay? And this is useful because it converts sort of Fourier analysis. We almost know nothing about G. It could be anything. The only thing we know is that the Fourier transform lives in P. And what we've done is we've converted it to sort of geometric data, added combinatorial data, right? We now know it's just a bunch of tubes. Constants. We don't know what the constants are. We could compute what they are, but of course those constants would depend on G, and that gives no, we don't know anything about G, so therefore we don't know anything about CT. Okay? But nonetheless, they're constants. But more importantly, we know that, we just converted it into some tubes. So, for example, and you can reverse this sort of, you could give a collection of tubes. Let's say it's like 5 here and 2 here, and let's say that G looks like this, right? That's one such valid G, right? Okay, so that's wave packet decomposition. Great. Okay. Let's see. So maybe, in the interest of time and the interest of reminding oneself later, let's prove an estimate And it won't be obviously related to the key estimate in the parabola S. It looks similar, but it won't obviously be related. But it does use wave packet decomposition. Okay. And then we'll relate it to the key estimate later. Okay, so let's prove the following. Okay, so remember, what's the goal? What's our next intermediate goal? Our next intermediate goal is to give a proof of the key estimate in this style of wave packet decomposition. The Bourgain diameter proof will make use of these wave packet decomposition, these things. So now remember our key estimate. Our key estimate said the integral of f theta I is bounded by nu to the minus big O of 1 times the sum of partition I into intervals length nu to the 2b Okay, this was the key estimate from which we were able to apply the definition of bilinear decoupling to go from AB to 2BB. And remember here, I is of length nu to the A, I prime is length nu to the B. The distance between I and I prime is at least nu. And of course, F is very transform supported in the very thin neighborhood of the parabola. Okay. Okay. So, and F is very supported in Okay. That's what we want to prove. Let's prove the following instead. Let box be any square of side length nu to the minus 2b. We will prove then the average, so let's write average, of f theta I squared times f theta I prime to the 4 is bounded by nu to the minus big O of 1 times the average value of f theta I squared times by the average value of f theta I to the 4 prime. Given all these assumptions on I and I prime, where I is of length nu to the A, I prime is of length nu to the B, and the distance between I and I prime is at least nu. Just because it makes it easier to think about, let's assume A is B. The same proof works. Okay. It's just that we'll have tubes of the same size, and you don't have to think as much. Okay. So I claim that this is true using the uncertainty principle. And probably next time I'll show how this estimate implies this estimate. But let's prove this estimate. Are there any questions?
The right side you have average twice. The
Yes.
left side only one.
Yes.
So, but still confused at all?
Yeah, actually, so what will happen is that later, how do you get from this estimate to this estimate? What you'll do is you'll use Plancherel in this estimate. Of course, Plancherel doesn't get rid of the average. But then you use the fact that, well, G is essentially constant on any translated T naught. Well, this also says G is essentially constant on any ball of radius R. And then you use the fact to basically merge the Fj inside here. Okay. So you really need to use, there is some little trickery with the uncertainty principle involved to show that this guy will in the end be the same as this guy. Yeah. Okay, but let's first show this one, because this one will follow from, you'll see some tubes, and you'll very obviously see that we'll actually use this bigger than or equal to new thing. Okay, so let's use that. Okay. Okay, so let's draw a picture. Okay. Here's I prime. We're not even going to bother to translate I prime to be at the origin, but the picture stays the same. Okay. Here's theta I prime. And associated to theta I prime, the left-hand point gives a vertical direction. Okay, and here's theta I. And the left-hand point gives a sort of direction that's pointing at a different angle. Okay? And we know that this length is at least nu. So if you're bored, you can think about how does this separation translate to the angle between the if knowing that these intervals are separated by length nu, what does this say about the angle between these two arrows? Okay, so f theta I is Fourier supported in theta I. Okay, so great, that's exactly what this is built for, right? So we're going to say then wave packet decomposition says that the absolute f theta I is basically some constants times some tubes. And what are the dimensions of these tubes? What do these tubes look like? Well, I is the interval length nu to the b. Right? So if we apply this lemma, what do the T-naughts say? The T-naughts are nu to the minus b by nu to the minus 2b pointing in the direction that the left-hand point tells us from. Okay, pointing in this direction. So in this dual direction. Okay? And they tile all of R2. Okay, similarly, and these tubes are disjoint. This is tiling. Right? So then we square it, and this squares it over here. Right? Because it's disjoint. Okay, similarly, f theta I prime to the 4 is, well, you do the same thing. Let's call it t prime and t of I prime. C t prime I prime to the 4, indicator function t prime. Right? And what do these things look like? These are nu to the minus b by nu to the minus 2b pointing vertically. Okay? Okay, so that's one thing. We've used the local constancy property. Which board should I erase? Okay. Now what? Okay, well, let's look at the average interval. Okay, so uncertainty principle tells us that this guy is just the sum t and ti, t prime and ti prime CT I squared, T prime I prime to the 4, and then let's average over the integral of the intersection. Right. All I did was combine these things and move the integral inside. Right. Now, of course, for free, these two tubes here must lie in this box. So you might pause for a moment and ask, why did I pick a square of size nu to the minus 2b? Right? Well, why didn't I pick a bigger square, or why didn't I pick a smaller square? Well, I didn't pick a smaller square, so here's, see, I picked nu to the minus 2b because this is the scale for which these tubes fit inside that box. Right? So the tubes, you know, this is a typical T, and this is a typical T prime. Right? And this is the right box to pick. If you picked a too big box, okay, then the picture looks like this. What am I doing? I could pick a smaller box. Okay, and if I picked a too small of a box, I don't see the whole data. Right? So this is why I picked the nu to the minus 2b box. I want to see it's the right scale to pick, because that's where the geometry happens. Okay. Okay. Next thing, for free, I can assume that both T and T prime live in, well, at least they intersect box. So I'm going to say live in box. Okay, let's say intersect box is not empty. Okay, they certainly have to touch box, because otherwise it's 0. Okay, so I can add that for free. And actually, furthermore, I can cheat and use, remember, we don't distinguish between 2R and R. Okay, so if I just have this condition, let's think about how the tubes and the boxes could interact. Okay, so here's my box, and if my tube lives here, then that's great. And this is most of the tubes, right? Most of the terms most of the terms in this sum are either 0 because they lie over here, or they're completely inside. Okay. So that would be great, right? They're either 0 or they're completely inside. Now there's this annoying edge case, right? What if they look like this? Well, this is of length nu to the minus 2b. This is nu to the minus 2b. So let's dilate this box by 100 times. Then it's contained inside. Then I'm back to, it being inside a box like this, right? Now remember, if I dilate a box by 100, well, that's the same as the box itself. Okay. So we can assume, actually, that both these tubes and tube prime are actually just contained in box, heuristically. Okay? Realistically, you have to actually consider this. Okay? And the way to get around this rigorously is that, okay, maybe this is like the main term, and you'd dilate this by powers of 2, and you'd get some exponential decay and stuff like that. Okay? This is the main term. Most of the situation is, these edge cases are annoying, and you do have to handle them. But most of the terms in this sum, without this condition over here, either it's a tube over here in the box, in which case it doesn't touch, or it's completely inside. And you'd account for at least 50% of the terms that way. Okay? So let's assume we just literally put in the condition that my tubes have to lie in the box. Yeah. So I don't have this I'm just 1 foot in, 1 foot out. Either I'm completely in or completely outside. Okay? Great. So, what does the picture look then? Let's draw the picture. Okay, so let's draw the picture. T is pointing in this direction. And so this is T. Let's see. This is T. And T prime is vertical for convenience. Okay, it doesn't have to be vertical. It could be some other. It could be right here. That's just be at least nu distance. So this is T prime. Okay. Furthermore, we know that this is nu to the minus b, nu to the minus 2b. This guy is also nu to the minus b, and this is nu to the minus 2b. And what do I want? I want to compute the intersection. Okay, well, this is high school geometry, or middle school, or I don't know about what level it is in Taiwan, but basic, right? So it's just you take this side and you divide it by, well, you take nu to the minus b times nu to the minus b and you divide by sine of this angle, right? And because these are separated by nu, this angle is at least nu, okay? So then, okay, so let's write it down. Okay, so since the distance between I and I prime is at least nu, the angle between t and t prime that are relevant in this term is also at least nu. So what does this say about t and t prime? The intersection is bounded by nu to the minus b squared, okay, and then divided by the angle. Well, the angle is at least nu, so we get that. Right, and so being very lazy, this is nu to the minus bounded times nu to the minus 2b. Okay? Yeah. Okay, great. And so therefore, what does this say? Well, this guy is then basically sum t and ti, t prime and ti prime, t and t prime must be inside a box, constants that I have no control over, just fine, times by, okay, so what's the average of the box? Well, the volume of the box is nu to the minus 4b, but it's 1 over, so I get nu to the 4b. Okay, and then times by the intersection, so I get that guy, so I get nu to the minus big O of 1, nu to the minus 2b. Okay, so what do I get here? I get that this is nu to the 2b. Okay, times nu to the bounded. Okay. So I know the left-hand side pretty well now, right? I've literally computed what it is. Okay, so now, so I know what this side is. Now I just want to compute this right-hand side. What is this right-hand side? I mean, it's also geometry. Okay. Let's put it down here. Let's swap these boards. Put this one down. Okay, and let's erase this board. Ooh. Okay, so now what did we want to do? We wanted to prove this estimate, right? So let's literally write down the right-hand side. Okay, so let's write it down. Right-hand side is nu inverse average times another average. Okay. Now we know what these guys are, so let's write it down. Let's even just insert the sum. Sum t and ti, cti squared, average 1t. And secretly, remember, we can add in the assumption that I'm completely inside the relevant box, because either it is not, or it's contained in it, or if it's touching, I just dilate the box and dilates don't matter. Okay. Okay. At least this guy should be bigger than that guy if we compute everything. Great, so let's compute it. What's the volume of a tube? Well, the volume of a tube is nu to the minus 3b. Okay, so let's hope for the best. Okay, so this is nu to the minus big O of 1. At least the sum is the same. T and ti, t prime and ti prime. These relevant tubes need to be inside my box. Okay, so you got two averages. Each average gives me a nu to the 4b. And then you got two volumes. Each volume gives me a nu to the minus 3b. Okay, and of course you have these constants, C2s squared. Great, and it matches. Right? That's a nu to the 2b. This is a nu to the 2b. Okay, great. So then that's a true inequality. Of course, you might ask, why didn't I write inequality here? Well, if you write it rigorously, it's an inequality. Yeah. But this is how people do these calculations on back of the envelope, right? How do you even know to prove this estimate first, right? You do a wave packet decomposition, you calculate the volumes. Oftentimes, an even easier trick to do is to assume that you have maybe not necessarily nuisance, but one separation. Right? Assume your intervals are transverse. You do these back of the envelope calculations. Do you have this estimate here? Right? Or how do you test if an estimate is true? Well, you try your wave packet decomposition. You plug in both sides, compute left-hand side, compute right-hand side. And if you can't even do that, well, then maybe even try setting your constants to be all 1 or something. Can you do that calculation? Right? And so I guess next time we'll talk about how this estimate will imply this estimate. Now, this estimate would go by the name of bilinear cacao. Right? I have two tubes, they intersect. This is cacao. Okay, I mean bilinear cacao in R2 is easy because two tubes, two rectangles of the same size pointing in different directions inside one region will always intersect, right? It's not true in R3, right? But yeah, this will show that, this shows that you do have some sort of cacao-like input if you want to use wave packet decomposition. This is not apparent in that proof that I showed you, which only uses lower dimensional decoupling. But all the Bourgain-Demeter style proofs will have some sort of cacao type estimate that will follow from multilinear cacao, generally speaking. Only in R2, it's just easy. Yeah. And then there's some uncertainty principle business to convert it to some estimate that you would want to prove. Yeah, okay, so that's it for today. So next time I'll finish up going from here to here. And maybe I'll start talking about paraboloid in R3. Yeah. Okay, are there any questions? Yeah. All right, well, that's it for today.